Alright, our goals for this lesson are evaluate trig functions using the sum and difference identities and to solve using double angle identities. So let's look first at the cosine of a sum or a difference. For the cosine of a sum or a difference, we'll have the cosine of x plus or minus y, and these are going to be angles. So cosine of some angle equals angle of x plus or minus angle of y. And we left with the cosine of x, cosine of y, minus or plus the sine of x, sine of y. So you got to note the sign switch. Cosine of x plus y is going to be cosine x, cosine y minus sine x, sine y. Cosine x minus y is going to be cosine x, cosine y plus sine x, sine y. So there's a proof of this on page 463 in your book if you're interested. So now let's look at an example. We want to find the exact value of the cosine of 15 without a calculator. So we have to figure out what angles that we're familiar with that add or subtract 15. So we can use the cosine of 45 minus 30. And then we can plug it into this formula we had, where we had the cosine of x is 45, cosine of 30, plus, notice the signs are different, sine of 45, sine of 30. And then we can evaluate using the square root of 2 over 2, square root of 3 over 2. And then our sine of 45 is square root of 2 over 2, and our sine of 30 is 1/2. We will multiply these together, and we'll get square root of 6 over 4 plus square root of 2 over 4. And we can simplify the square root of 6 over plus square root of 2 over 4, and there's no additional simplification that we can do here. So let's look at another example. We have the cosine of 75. So we want to use, this one is a larger value, so we'll probably use the sum. Well, the sum of 45 and 30, 45 plus 30 is 75 degrees. So we'll use the cosine of the sum of these two angles. It's cosine of 45, cosine of 30 degrees, minus sine of 45 degrees, sine of 30 degrees. And then we can evaluate each of those. Cosine of 45 we know is the square root of 2 over 2. And then square root of 3 over 2 minus square root of 2 over 2 times 1/2. Multiply these together and we'll get square root of 6 over 4 minus square root of 2 over 4. And simplify square root of 6 minus square root of 2 over 4. Now notice this one looks a little similar to the last one, but the reason being it's different is there's sum here, and the last one was the difference. So now let's look at the sine of a sum or a difference. So for the sine of sum or difference, we'll have the sine of x plus or minus y equals sine of x cosine y plus or minus cosine x sine y. Here our signs are going to stay the same. So when you have the sine of a sum, their parts are going to be added together. What's different is the order in which the angles are evaluated. So in the first one, you evaluate sine of x cosine of y. In the second part, it's cosine of x sine of y. So make sure you notice that switch. There's a proof of this on page 465 if you're curious or would like to look at it. And so now we want to find the exact value of the sine of 15 degrees. So for the sine of 15 degrees, we can use, just like we did for the cosine, we can use 45 and 30. And we'll have the sine of 45 cosine of 30. Notice we're using our now sine of a sum or difference. And then the signs stay the same, cosine of 45, sine of 30. Then we can evaluate those like we're used to using the unit circle. Square root of 2 over 2, square root of 3 over 2, minus square root of 2 over 2 times 1/2. Multiply these together and get square root of 6 over 4 minus square root of 2 over 4. And then you'll be left with square root of 6 minus square root of 2 over 4. Now notice this looks very similar to the last answer we got here. Reason being, 75 and 15 are complementary angles. They add to 90. So the sine is going to be equivalent to the cosine. That's using your cofunction identities. So that's important to remember. Now let's look at the tangent of a sum or a difference. So the tangent of a sum or a difference, we know tangent is sine over cosine, so we can actually use these sum and difference identities within the tangent as well. The tangent of x plus y plus or minus y is sine of x plus or minus y or cosine of x plus or minus y. So these will follow the sum or difference as before. Or you can use the one for tangent, which is tangent x plus or minus tangent of y all over 1 minus or plus tangent of x plus tangent of y. So when you're using the sum here, you're going to have a plus up top, minus on the bottom. When you're using the difference here, you're going to have a minus up top and then a plus on the bottom. Okay? There's a proof of this on page 467 if you're interested in looking at it. So now let's look at an example. We have the tangent of 5 pi over 12. So this one you're going to have to look a little bit harder maybe to find what your angles are. So for here, we have the tangent of 5 pi over 12. And so I separated that to tangent of 3 pi over 12 plus 2 pi over 12, which simplifies tangent of pi over 4 plus pi over 6. So using this, we can use either the tangent or the cosine identity. So we're going to start by using the tangent identity. So for the tangent identity, let's get a little blurry again. Tangent identity, we'll use tangent of pi over 4 plus tangent of pi over 6 minus all over 1 minus tangent pi over 4 tangent pi over 6. Notice that since this is a sum, you're going to have the plus at the top and the minus at the bottom. Now, tangent of pi over 4. At pi over 4, it's sine over cosine. So you're going to have tangent of square root of 2 over 2 divided by square root of 2 over 2. And then for tangent of pi over 6, you're going to have sine over cosine again. You'll have the square root of 3 over 2 divided by 1/2. And then you'll be able to, or square root of, you'll have 1/2 divided by square root of 3 over 2. So then we'll get 1 for tangent here. Then tangent here is going to be square root of 3 over 3. At the bottom, same, 1 and square root of 3 over 3. I can multiply top and bottom by 3 over 3 to reduce those fractions. And I'll get 3 plus square root of 3 all over 3 minus square root of 3. Multiply by its conjugate to get rid of that radical in the denominator. And I'll get 9 plus 6 square root of 3 plus 3 all over 9 minus 3. And then that's going to give me 12 plus 6 square root of 3 over 6, which simplifies to 2 plus square root of 3. Now, we can also use the sine or cosine identities to solve this as well. So here we'll have, this is our sine identity on top, this is our cosine identity on the bottom. Notice sine, since it's a sum, the sign is positive, and then cosine, since it's a difference, it is negative. So here we'll have the sine of pi over 4, cosine of pi over 6, plus our cosine of pi over 4, sine of pi over 6. And then on the bottom, using our cosine identity. You can evaluate those at each part, and then multiply by 2 over 2 to kind of simplify those fractions. And multiply them together, and I got square root of 6 plus square root of 2, square root of 6 minus square root of 2. Multiply by the conjugate to get rid of that radical in the denominator. And you'll get 6 plus 2 square root of 12 plus, this is a 2 here. That's a little hard to see, I'll rewrite it, plus a 2. And all I did was just distribute. And here's difference of squares, so I know I have 6 minus 2. And that gives me 8 plus 4 radical 3 over 4. And again, I simplified 2 plus square root of 3. So I get the same answer, they're just using 2 different methods. Alright? So the next part of this lesson is going to be our multiple angle identities. So we're going to start with our double angle identities. We have the sine of 2u, and the multiple angle identities come from our sum and difference identities. So let's look at sine of 2u. We can rewrite it using our sum identity as the sine of u plus u. We'll have sine of u cosine u plus cosine u sine u. It ends up being 2 sine u cosine u. So it's always going to work for your double angle identity. This is what you can substitute using for sine. Cosine, you have cosine of u plus u, and again I used that difference identity, so I plugged it into the difference identity and got this. Cosine u, same as cosine squared u. Sine u, same as sine squared u. So this is my first identity. But I also know with the cosine squared of u is also equal to 1 minus sine squared u. So I substituted that in, and then I simplified, and got 1 minus 2 sine squared u. But I also know that sine squared of u is 1 minus cosine squared of u. So I substituted that in, and got 2 cosine squared u minus 1. So these three are all double angle identities for cosine of 2u. where u is your angle or single angle and 2u is the double angle. Okay, so let's look at an example. So I have sine of 2x equals cosine x on this interval. I went ahead and put in my double angle identity, 2 sine, this is like our u, 2 sine x cosine x equals cosine x. Now I can subtract cosine x from each side, so I'll have 2 sine x cosine x minus cosine x equals 0. Here I can factor out a cosine x, so I have cosine of x times 2 sine x minus 1 equals 0. And then from here, like we used before in solving trig identities, I can use my zero product property. I have cosine of x equals 0 or 2 sine of x minus 1 equals 0. So cosine is 0 at x equals pi over 2 and 3 pi over 2. And this one we can solve. So sine of x equals 1/2. So sine is 1/2 at pi over 6 and 5 pi over 6. And all of these are no restrictions on my domain other than it being between 0 and 2 pi. I don't have any additional restrictions. So my answers are x equals pi over 2, 3 pi over 2, pi over 6, and 5 pi over 6. So this one has 4 answers. Okay. And then I have one that I would like you guys to try. So this one, we have the sine of 2x plus sine of 4x equals 0 on the interval of 0 to 2 pi. And my hint to you is that you have the sine of 2x plus the sine of 2 times 2x, so you're going to use that double angle identity 2 times. So 2 times for that double angle identity, you'll use it once here and you'll use it once again. And in the end, you should get 0, pi over 3, pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, and 5 pi over 3. So make sure you can go through this and get these answers, and I will check it tomorrow. And now let's look at the half angle identities. So for our half angle identities, these are when you can divide your angle by 2 and get something that you're used to working with. So here for sine of u over 2, we're going to have plus or minus square root of 1 minus cosine u over 2. Cosine u over 2 plus or minus the square root of 1 plus cosine u over 2. It's important to remember that these plus or minus. For tangent, you can use any one of these 3. You can use plus or minus the square root of 1 minus cosine u over 1 plus cosine u. You can use 1 minus cosine u over sine u. And you can use sine u over 1 plus cosine u. Different values or different problems might lend you to use different problems. Or different forms of this. So we want to use these just like we use our double angle identities. We want to use them to solve for some angles when the sum doesn't work so well. So we want to use the half angle identity to find the exact value of pi over 8 without a calculator. So here, pi over 8, we got to figure out what can we divide by 2 to get pi over 8. So this is the same as pi over 4 divided by 2. Okay? So now our u equals pi over 4 when we're doing u over 2. So we had one identity for sine, and that was 1 minus cosine of u, where u is pi over 4 all over 2. And we know that the cosine of pi over 4 equals the square root of 2 over 2. And then we can multiply top and bottom by 2. And we'll get plus or minus the square root of 2 minus square root of 2 all over 4. We can separate the square root over our top and bottom. So plus or minus the square root of 2 minus square root of 2 all over, and then the square root of 4 is 2. And then we got to think, well, what quadrant are we in? So, is it positive or negative? Well, pi over 8 is in quadrant 1. Okay? Cosine, or sine, sorry, sine is positive in quadrant 1. Okay? So that means our final answer is going to be positive, so we just have square root of 2 minus square root of 2 all over 2. So this is why our answer is positive. So we don't need to use the negative. Okay? So now I have one for you to try. I want you to try this one. We have sine squared of x minus 2 sine squared of x over 2. And this is where you're going to use your half angle identity. And you'll be able to just substitute it in, because you can also write this as sine of x squared equals 2 times sine of x over 2 squared. So remember that these can be written, these mean the same thing. So this is going to help you, this should help you solve this problem. So make sure you can get these answers. This one I wanted you to solve for all values. So you should be able to get pi over 2 plus pi k and 2 pi k, where k is an element of z. And I'll check this one tomorrow as well.